Hey, welcome back. This is now 12.4. We're going to work with the unit tangent vector and the unit normal vector, the principal unit normal vector in particular. We'll begin with the unit tangent vector. So the unit tangent vector is essentially just going to be the velocity vector, but resized so it has length 1. Okay, so given some vector value function representing a smooth curve, we will define the unit tangent vector to be the derivative of that r thingamajig there divided by the magnitude of the derivative of r. Okay. So we need the smoothness that will, that not only does it ensure issues of continuity, but it ensures that the r prime is not equal to the 0 vector. So you won't have an issue of division by 0 when you get that magnitude there. Okay, so finding this thing can be computationally exhausting, to say the least. Let's look at example 1. So we have r of t equals t comma t squared. Okay, so I find r prime of t is going to be 1 comma 2t. Find the magnitude of r prime of t. It's going to be the square root of 1 plus 4t squared. And then you could form your unit tangent vector t. That will just be 1 all over the reciprocal of the magnitude of r prime of t times r prime of t, right? The book will kind of keep it out in front as a coefficient. I like to distribute it through the vector, so I end up with 1 all over 1 square root of 1 plus 4t squared, comma 2t all over square root of 1 plus 4t squared. So at least at this time, that one wasn't so nasty. They also want you to evaluate the unit tangent vector when t is equal to 1. So t of 1, just plug 1 in for t. You get 1 over root 5. 1 plus 4 is 5. And then 2 all over root 5. Okay, so no big deal there. You can draw a little picture of it. So in this case, from the r of t function there, x is equal to t, y is equal to t squared. Eliminate the parameter, so y would equal x squared, and that's just a parabola. At 0, it's at 0, 0. At 1, it would be at 1, 1 here. So the orientation is in this direction. Then the unit tangent vector at 1, 1 would look like something like this, and it would have length 1. Okay, so that's the big and the small unit tangent vector. It points in the direction of travel. So just what they're talking about here on the right, in example 1, they can play around with it and make the curve have the opposite orientation. In that case, if you got the unit tangent vector, it would be pointing in the opposite direction. Okay. They have some questions where they're asking you to first find the unit tangent vector and then get the parametric equations of the line. So like number 10 in WebAssign is of that flavor. So here they are. So r of t is t squared, comma t, comma 8/3. And then our point is 4, 2, comma 8/3. And first they want you to get the unit tangent vector and evaluate it at t equals 2. Or not, yeah, t equals 2. So first go ahead and get the derivative. 2t, comma 1, comma 0, apparently. Get the magnitude of that. It's going to be the square root of 4t squared plus 1. And then I like to just distribute it into the vector here. So I end up with 2t all over the square root of 4t squared plus 1, comma 1 all over the square root 4t squared plus 1, comma 0. getting then our t value at 2. So I'm just going to plug 2 in for t. I get 4 all over the square root of, it looks like 17. And then 1 all over the square root of 17, 0. And the unit tangent vector will point in the direction of travel. So, and also it's tangent to the curve. Okay, so if you want to form the parametric equations for the line that's tangent to our curve, you can use this vector as the directional vector for your line, right? So if you were to create the vector value equation for the tangent line to the curve at 2, it would look as follows. So you can multiply this vector by root 17 and just have 4, 1, 0 for your directional vector t, and then add it to your starting position, a vector pointing at the point 4, 2, 8/3. They want it in parametric form, so all you have to do is kind of pick out the, what happened? Did I accidentally go backwards? Have to pick out the x component and the y component. So you could rewrite it as 4t plus 4, t plus 2, and then 0t plus 8/3. And you see that would be, you know, the answer they want. So x would be 4t plus 4. It's a bit redundant, but well. Okay, so those would be the parametric equations of the line that's tangent to this curve at the point 4, 2, 8/3. Okay, so I guess it's kind of an application, sort of. I don't know. Oh crud! I just clicked off the book. All right, 1 second. I got to open the book back up. Hopefully it'll send me back to where we were. No. Okay, whatever. So 12.4. Okay. Okay, so there's that. What else do we need to worry about? Okay, now we're going to get into the unit normal vector, in particular the principal unit normal vector. So at any point on the curve, there's actually 2 normal vectors, and these things are perpendicular to the tangent vector. So let me draw one in red. The one in red is the one we want. Okay, so we want the one that's pointing sort of to the inside of the curve. So if I was traveling around on this parabola, I'm kind of going to the inside, not to the outside. Okay, so that's the principal unit normal vector that I'm after. So this is the unit tangent vector. The principal unit normal vector that I want is this guy right here. But there are 2 of them, right? There's another one that goes in this direction, but we don't want that one. Okay, so one thing to notice from my little picture here is that the unit normal vector and the unit tangent vector are perpendicular. Okay, the way we compute the unit normal vector. So here, let me set that up. Okay, so section 2, the principal unit normal vector. The way we compute that is from the derivative of the unit tangent vector. So if you think about the unit tangent vector being a derivative of the position vector, you kind of think, well, isn't the normal vector just the acceleration vector? And that's not going to necessarily be the case. Okay, so the acceleration vector is not necessarily going to be perpendicular to the tangent vector, but the normal vector is perpendicular to the tangent vector, and that's what they're doing in the book here in the middle of on the right side here, where they go so anyways, let's first introduce the thing. So the principal unit normal vector is going to be n of t equals the derivative of the unit tangent vector divided by the magnitude of the unit tangent vector. Okay. And my claim is that these guys are perpendicular. In other words, n dotted with t is going to equal 0. Okay, so how do I prove that? Some proof. Well, you can think about the dot product of the unit tangent vector. So we note t dotted with t is just going to be the sum of the components squared, right? And if you think about the magnitude of t, that's the square root of the sum of the components squared. So this t dot t is actually just the square of the magnitude of the unit tangent vector. Okay? And because it's a unit tangent vector, we know its magnitude has to be 1. Okay? Okay, take the derivative of both sides of that equation. Okay. On the left-hand side, the derivative with respect to t of t dot t, we can use some of the derivative rules from 12.2 to rewrite that. And if you remember the rule, it's kind of like a product rule with dot products. So it'll be t dotted with the derivative of t plus t's derivative dotted with t. Okay. Because the dot product is commutative, you can then rewrite that as 2t dot t prime. Okay. Then note the other side, noting the right-hand side. The derivative with respect to t of 1 is equal to 0. Hence, we have the equation 2t dot t prime is equal to 0. And you can multiply both sides by 1/2, the scalar, and you end up with t dot t prime equaling 0. Okay, and that indicates that these two vectors are perpendicular. So hence, sorry, I hit my mic button, sitting on it. Hence, t and t prime are perpendicular, or orthogonal. We note n is just a scalar multiple of t prime, right? It's just t prime all over the magnitude of t prime. In other words, the normal vector is going in the same direction as t prime. So in other words, the normal vector is just a scalar multiple of t prime, and thus it must then be the case that t dotted with n is equal to 0, and which implies they are perpendicular. Okay, so something along those lines. They kind of sketch the proof right here. There's probably little issues I'm not worrying about, but yeah, that's the big kind of a fleshing out of what this one line is really indicating. Okay, so this is the one that becomes annoying computationally, and if you're going to be making mistakes, it'll probably be because of this character. So anyways, let's look at example 3 and kind of see what we're up against. Find n of t and n of 1 for the for this guy. Find n of t and n of 1. Okay, so first we need the unit tangent vector. So it's going to be 3, 4t. Magnitude. And the square root of 9 plus 16t squared. And then the unit tangent vector will be 3 all over the square root of 9 plus 16t squared, 4t all over the square root of 9 plus 16t squared. For the unit normal vector, I need to get the derivative of that chunk, right? So that's where it becomes a nightmare. The book will kind of work with the reciprocal of the magnitude of r prime of t, and then use the derivative rules from 12.2. You could say using theorem 12.2. I just do brute force. I don't see how that is any easier, what they've done. So I'm just going to use brute force and take the derivatives. In particular, I'll note that this first component is just 3 times 9 plus 16t squared to the negative 1/2. And so I'll have negative 3/2 times 9 plus 16t squared to the negative 3/2 times, and you get a chain rule there, so 32t. And then the other guy got to go low to high minus high to low. So low, 9 plus 16t squared to the 1/2. D high is 4 minus high. 4t times the derivative of the low, so that would be 1/2 times 9 plus 16t squared to the negative 1/2 times 32t from the chain rule divided by the denominator squared, so you get 9 plus 16t squared. Leave myself a little bit of room because I'm going to be simplifying that behemoth. And I'll multiply top and bottom to get rid of that negative 1/2 exponent. I'll multiply top and bottom by 9 plus 16t squared to the 1/2. Okay. 9 plus 16t squared to the 1/2 eventually. You probably want to clean this up a little bit before you do that. All right, so before I do that, I'm just trying to save time. I wouldn't want you probably to do your homework like this, where you're doing all kinds of little arrows and circles. It would be a mess, and you'd probably make a lot of mistakes. But try to keep your work organized, unlike what I'm doing here. Okay, so if you simplify that numerator, you're going to have 4, 9 plus. Well, do I need to? Am I really that bad off? I need to do that. Let's see where I am. Okay. So in the top, it looks like I'm getting 2 into 32 is 16 times 3 is negative 48t all over 9 plus 16t squared to the positive 3/2. This behemoth thing, if I distribute this character, in the first distribution, you just end up with 9 plus 16t squared times 4. And in the second distribution, let's clean it up a little first. So 2 goes in the 32. That would be 16 times. 4 times 16. 4, 2 is, we're getting a negative 64 right there. This thing times this thing right here, those will cancel each other out, right? Those are inverses of each other. And then we have a t here and a t here, so that would be t squared. And then all over 9 plus 16t squared to the first plus 1/2 is 3/2. Oh, that's not so bad, right? And then you get negative 48t all over 9 plus 16t squared to the 3/2, comma, this numerator is 36 plus 64t squared minus 64t squared is just 36. Then 9 plus 16t squared to the 3/2. Okay, that's just for t prime. Now I need to get the magnitude of t prime. And so big root of 48t, negative 48t, but when you square it, it's just going to be positive 48t plus 36 squared all over. They'll have a common denominator, so that would just be 9 plus 16t squared to the 3/2 squared will just be 3. Okay. And then maybe we can simplify a little bit and rewrite that as square root of 48t squared. And for some reason that seems wrong, but 48 squared t squared plus 36 squared. Those numbers just seem wrong. all over 9 plus 16t squared to the 3/2. Then basically you're taking this thing and taking its reciprocal and multiplying it on this thing, because this thing was your t prime of t. And the normal vector that we seek is the t prime of t all over the magnitude of t prime of t. Okay? So I take the reciprocal, and when you take the reciprocal, that denominator that's in t prime of t is gonna cancel out with the denominator of the magnitude of t prime of t. Right? So you're going to end up with, for your normal unit, your principal unit normal tangent vector, as being negative 48t all over the square root of 48 squared t squared plus 36 squared, comma 36 all over that same thing. Which seems awfully wrong to me. Does 4 go into those? So I bet you could factor out like a 4 or something, maybe even can you factor out anything more? Maybe even no. Trying to figure out how much I could factor out of that thing. It's like, what's common to 36 and 48? So you can take out a 6, certainly. Can you take out a 36? Yeah. So let me get my calculator. I want to simplify that because it's just, it looks like a nightmare scenario. 48 squared divided by 36, 64. So you can at least factor out 36, which will become a 6, and then you're left with 64 t squared plus a regular 36, but then you're going to be able to get more out of it, right? So again, we have 64 t squared plus 36. You can get a 9 out of it on top of it then, so you can factor out 3 really, so this would be like an 18. Negative 48t, 36 all over 18. So factoring that out then, 9, so that would be 4 here. So you could pull out even more. So geez, oh man, 64 divided by 9. Oh no, I'm wrong. I don't know what I'm thinking. So 8, 2. You could factor out 4. That would be. I apologize. This is becoming crazy. So that was true. You could factor out the 6, but then on top of that, you could factor out a 4. And that leave you with like a 9, and then 4, 1, 6. So 16t squared. And then, what did I say I factored out? A 4. So a 2 could come out, so you get a 12 here and a 12 here. 16t squared. There has been an easier way than that. So anyways, you'll get negative 4t all over the square root of 16t squared plus 9, comma, it looks like a 3 all over the square root of 16t squared plus 9. And it's nice simplified form. Drum roll, please. Let's see if that's what they got. Yeah, pretty much. Okay, so then I got to evaluate it at 1. I think that's what they're saying. And a 1 maybe. No, they just wanted you to find them. Oh yeah, no, they wanted 1. Okay, so what is n of 1? Negative 4 all over 25, so that would be 5, and then 3 all over 25, square root 25 is 5. Okay, great. The spiel that's coming up though right here when they start talking about if you're dealing with a plane curve, there's a relationship between the unit tangent vector and the normal vector because they're perpendicular, right? So note the unit tangent vector up here, I guess, to the right here. Unit tangent vector, the way the book did it is a little bit different, right? So t of t, let's go ahead and distribute that thing. Square root of 9 plus 16 t squared, comma 4 all over the square root of 9 plus 16 t squared. I guess should have, somebody is blowing up my email right now. Anyways, I guess maybe I could have simplified here or something. I don't know what became such the, I don't know why my numbers got so weird. Anyways, if you look at t of 1, what do you get? Well, you get 3/5, 4/5. So do you see? There is some sort of relationship. They're like perpendicular, right? So negative reciprocal kind of idea. You just flip the, well, in this case, the components, and you make one of them negative. There's two possibilities. So like I said back here with the picture, there's two unit normal vectors. You need the principal one. So you could just kind of guess, like flip the components. So there would be another, unit normal vector, we'll say n sub 1, which is going to be 4/5, comma, negative 3/5, right? I mean, there's two possibilities, and you could literally just flip a coin to figure out which one it is. But the way you should be going about it is from looking at the graph. Okay, so you can kind of avoid. Whoops, I got somebody in my email, so hold on. Hello, can you hear me? Okay, sorry, somebody interrupted me. Not interrupted, but okay, so right, we're trying to figure out how to get that unit tangent normal, the principal unit normal vector without having to worry about all those hardcore computations. And what I'm saying is that you can avoid it by taking advantage of the fact that these vectors are perpendicular to each other, orthogonal. So you'll see them talking about that in the book, like right here, okay? And then, as I was saying, it's all you have to really do is swap, and it's literally like taking the negative reciprocal. And somebody said that in my office hours, and I was like, no, it's not the. It is. It's basically just like taking the negative reciprocal. You're swapping the x and the y, and you make one of them negative, right? The problem is there's two of them. There's two possibilities, whether you put the negative with the x or the y. So you have to figure out which one it is, and the only way I can determine to really figure that out is to graph the thing. Okay, so you have to kind of come back here to these guys and say, okay, let me copy them down here so I can draw a picture. Where are you? So our t is 3t comma 2t squared. It looks like a parabola, right? So x is 3t. T is x over 3, and y will be 2 times x over 3 squared, so 2x squared over 9. Yeah, so some sort of parabola. At 1, we'll be at 3, comma 2. 1, 2, 3, comma 1, 2. And our tangent vector is positive, positive. So you kind of build it using the components, positive component x, positive component y. So it'll be over in the x direction and then over in the y direction, and you should be able to kind of build your unit tangent vector that way. So that's t. And then for the unit normal vector, you want the principal one. So you want this red one that's pointing to the inside of the curve, kind of in the direction of travel. So in order to pull that off, you need the normal vector that has components where the x component is negative, because you're going in the negative direction, and then the y component has to be positive, okay? So this thing, if you just look at the signs, it's going to be negative, positive. based off of the fact that the unit tangent vector is in the picture, basically the picture. Okay, so the one we have to pick is the minus plus one, and that's the one we figured out computationally through that big long process, the minus plus one. But you're going to be able to cheat with this process so long as you can graph it. Okay. The problem then becomes, well, what happens when I have a curve in space and it's not just a matter of taking a negative reciprocal, right? Yeah, that's an issue, and I don't know how to reconcile that issue beyond going through the computations. So I'll just warn you, I did put one of those in the homework. Okay, there is one there, and it's a bit nasty. So which one is it? It's number 4. So number 4, you may even want to just skip it if you don't have time to fool around, but that is probably one of the longer problems. And the longer you get, the more error you can expect to see. Okay. Okay. So the space curves, you cannot pull that trick. Okay. You cannot pull that trick. But any other kind of curve, you can kind of pull that off. 1 second. Hey. Okay, sorry, where was I? So example 4 gives you one of these 3 component space curves. The computations in this example aren't so bad, but I'm pretty sure that I could go over it real quick. I'll do question 3. So at least you have something to look at. No, it's question 4 is the annoying one. So if you want to, you can fast forward the video, but just be aware this problem, I think, turns out to be a little bit annoying. So let's take a look. R of t is square root 2t, e to the t, e to the negative t. They want you to evaluate the unit normal, principal unit normal vector at 0. So find that and then find this. Okay. So there's no way to cheat this, like just doing a swap of components. You literally, in my opinion, have to do brute force. So first get the r prime, that would be root 2, yeah, e to the t, and then negative e to the negative t. Magnitude of that character is going to be square root of 2 plus e to the t plus e to the 2t, e to the negative 2t. You got to square those. Believe it or not, that thing can be simplified. It's just e to the t plus e to the negative t squared, and then that's e to the t plus e to the negative t. E to the negative t. So our unit tangent vector is going to be square root 2 all over e to the t plus e to the negative t, then e to the t all over e to the t plus e to the negative t, and then negative e to the negative t all over e to the t plus e to the negative t. Then I need to find the derivative of that guy, so t prime of t is going to equal, so the first guy, I'm going to rewrite it, it's root 2 times e to the t plus e to the negative t to the negative 1. Okay, take the derivative of that, so negative root 2 e to the t plus e to the negative t to the negative 2 now, and then times the derivative of the guts, so that would be e to the t minus e to the negative t, the chain rule, and then comma quotient rule. Okay. So low times the derivative of the high minus high times the derivative of the low, all over the low squared, then low times the derivative of the high minus high, so that would become plus, is the derivative of the low, all over the low squared. And then I need to clean that up. All right, so I get negative root 2 e to the t minus e to the negative t all over e to the t plus e to the negative t squared, comma, distributing this thing, e to the 2t plus 1 minus e to the 2t plus 1. So you're just going to get 2 in the numerator once everything is said and done. And then here, this is going to be like the same deal, right? So you get 1 plus e to the negative 2t. Here, this is 1 minus e to the negative 2t. So again, you're going to get 2 all over e to the t plus e to the negative t squared. Then I need to get the magnitude of that. So the magnitude of t prime of t is going to equal big square root of, this will become 2, negative square root 2 squared is 2, and then I need the FOIL, this e to the t minus e to the negative t squared. So let me just write it out. And then it's going to be plus 4, and they have a common denominator, so I can just square that, e to the t plus e to the negative t to the 4th. This rigmarole will become 2 times e to the 2t minus e to, so minus 1 is minus 2 plus e to the negative 2t, and then plus 8 all over this stuff to the 4th, and then we get 2e to the 2t plus 2e to the negative 2t. Minus 4 plus 8 will be plus 4 all over e to the t plus e to the negative t to the 4th. Seems like I'll probably be able to factor that numerator maybe. If you factor out the 2, you get like 2 times e to the 2t plus e to the negative 2t plus 2. And that thing seems like it's a perfect square trinomial. Right. So I think we can rewrite that as 2 times e to the t plus e to the negative t squared all over e to the t plus e to the negative. Oh, there's a nice cancellation there, isn't there? To the 4th. So this would really just be root 2 all over e to the t plus e to the negative t, like that. That seems too good to be true, right? Anyways, let's go ahead, and I gotta, to get the normal unit, principal unit normal vector, I need to multiply the reciprocal of this thing onto this thing right here, and you're gonna end up with then negative root, the root 2's will cancel in the reciprocal, so you just get negative e to the t minus e to the negative t, and then one factor of the e to the t plus e to the negative t will cancel, and you just get e to the t plus e to the negative t. And same for this next guy, so it's 2 all over root 2 times e to the t plus e to the negative t. And then again for this, 2 all over root 2 times e to the t plus e to the negative t. Okay. Where are we supposed to evaluate this thing at? N of 0? That should be pretty easy. So plug n of 0 is plus 0 into that thing, and you're going to get, if you plug 0 into the first one, that's just going to be 0, because you get e to the 0 minus e to the 0. 1 minus 1 is 0, so that first guy is 0. And you get 2 all over root 2 times e to the 0 plus e to the 0 is just 1 plus 1, which is 2. And then 2 all over root 2 times 2. Okay? So it looks like I'm getting 0, 1 over root 2, and then 1 over root 2. Okay? Let's see if that's vaguely familiar compared to what we got. Yeah, that's what I got. Okie dokie. So yeah, computationally kind of nasty. Okay, but that's a good thing. That means there's work out there for you, for young budding math people and programmers trying to find new ways to figure these out quickly, right? If there's just some way I can swap the components or something like that, you know, that make these computations way easier. For me personally, I don't know. I just do brute force. I've never really sat around and studied it. I got better things to do. You know. So anyways, there's that. I don't really know if I have anything better to do, but I haven't been able to find out anything yet as far as simplifying that one. Anyways, moving on. I guess section 3 maybe. Did I give a section for the unit normal principal, unit normal tangent vector? Yeah. Okay, so there's that. Section 3 is going to be about acceleration. So we're going to describe acceleration in terms of the unit tangent vector and the unit normal vector. Basically, if you've been kind of following along with all of the physical properties of acceleration and velocity, the acceleration vector is not necessarily orthogonal to the tangent vector, right? So what we'll do is describe the acceleration vector in terms of the tangent and the normal vectors. The tangent and the normal vectors sort of become like the axes which describe the acceleration vector. Okay. Okay. So, anyways, tangential / normal components of acceleration. Basically, you kind of just remind yourself if you're given some sort of curve, the derivative of this thing is, you can also think of that as the velocity, and then the derivative of that again is then the acceleration. Okay. And we're trying to describe the acceleration in terms of the unit tangent vector and the normal vector, and what we'll have are these components that act like sort of coefficients of this thing that we're going to build. The formulas for those guys, there's a bunch of them, and the way I approach, or the way I think you should approach it, is you're kind of thinking of, I have a bunch of routes to get home. What is going to be my quickest route home, so I don't have to spend all kinds of my time on my commute? I don't want to be sitting in my car all day long. I want to find the quickest way home. And if you look over here to the right in Theorem 12.5, they give you the formulas for these components. And you see 2 of the formulas include the unit tangent vector and the unit principal normal vector, which you should have a distaste for at this point. So you try to avoid having to do that at all costs, because you don't want to spend 3 hours finding a principal unit normal vector. So you pick and choose. Pick your poison, pick it. Hopefully you find a way to pick it and kind of avoid spending 3 years doing computations, right? So let's take a look at some of these problems. So look at example 5, I guess. And they give us the curve 3t, -t, and t squared. And I'm thinking there's like no way I want to go through the unit normal vector with another space curve. So I'm hoping I may be able to pull off like that dot product formula they have for the tangential component. So in order to get that dot product, you need the velocity and you need the acceleration. So the velocity again is just r prime of t. So that would be 3, -1, 2t. I'm going to need the magnitude of that for to get the to plug in for the formula. So that's the square root of 9 plus 1 is 10 plus 4t squared. And then I need the acceleration for that dot product. So A of t, you forgive me if I forget to put little arrows over top. So the dot product is going to be, sorry, acceleration, 0, 0, 2. Okay, so let's get the dot product. So V dot A and is going to be 0 plus 0 plus 4t. So the tangential component is going to be 4t all over the square root of 10 plus 4t squared. Okay, I can put that into, there's a, over here to the right, you see a square root formula for the normal component. That looks like a nightmare if I had to square this thing, and then I'm working with, that might not be so bad, but it looks like it's going to be a lot of work. So instead I'm just going to do the cross product, because doing a cross product with something that has 2 zero components is kind of easy. So V cross A, I, J, K, 3, negative 1, 2t, and then 0, 0, 2. So it's just going to be coming up the first column, negative 2, comma, second column, negative 6, and then the third column, 0. The magnitude of that, which I need for the formula, is going to be the square root of 4 plus 36, which is square root of 40, so that's 2 root 10. And then I had the magnitude of the velocity up here already. So A sub t, I got A sub n using the formula with that cross product is 2 root 10 all over the square root of 10 plus 4t squared. Okay. So it should give me my two formulas that they're after. Let's see what they get. Yeah, they got the same thing. They use the same formulas, so it's a good choice. Let's move on to another one. So this one, example 6. There's more than one way to do it, right? Any formula you use, that's what they're saying here in example 5. You could have used the alternative formula. Yeah, any formula you use, you're going to get the same answer. It's just one may take you longer than the other. Anyways, example 6, they're giving a circular helix. R of t is b cosine t, b sine t, and then ct. I'm going to come back here and kind of look. I definitely still do not really want to do the normal, get that unit principal normal vector. No way. I stay away from that like the plague. Let's get the velocity and the acceleration and see what we're doing. So again, negative b sine t, b cosine t, and then c. The acceleration then is going to be negative b cosine t, negative b sine t, and then 0. So the tangential component, v dot a, so that's going to be v dot a, that's going to be, man, I hope my microphone was not off the entire video. Oh my God. Okay, sorry. So v dot a is b squared sine t cosine t, and then plus, well, it would be minus b squared cosine t sine t, and then plus 0 all over the square root of something that I don't really need to compute because the numerator is 0. So that component is 0. Let's get the normal component. So that component, I could do the cross product of these two vectors up here. But I think it would be easier to just go after, use that square root formula. So the magnitude of the acceleration is going to be b squared cosine squared t plus b squared sine squared t. Then you can factor out the b squared, and you just get cosine squared plus sine squared, which is 1. So you get the square root of b squared times 1, which is just b. Okay. So we'll have the square root of b squared minus the tangential component squared, which was just 0. So you're just going to end up with b for your normal component. We'll make that one the video quiz as well. Video quiz, video quiz, video quiz, video quiz. Okay. Okay. So lots of computation. You can see down here that they can get pretty nasty with regards to your fractions and square roots over here on the right. And you'll get some of those problems down here. Like number 6 is kind of annoying. Number 7, also annoying. Number 8, kind of annoying. Okay, so computationally, yeah, you're going to want to make sure you're doing your work in an orderly fashion. Eliminate, especially when you have a hard problem, you may want to pause the music, give that a pause, get a quiet room, eliminate distractions, have plenty of paper, to be very organized, anything you could do to prevent, making a mistake. And, in the real world, they'll tell you, like the engineers and everybody, they don't learn how to build bridges by kind of trial and error, and maybe the software is bad in that way because you just put in the answer and push enter and see what happens. You can't do that with a bridge, so you want to get it right the first time. You want to know what you're doing. So you can imagine being a computer programmer and you're programming all day long and you barely even know what your code does, but you hit the compile button and it works. That's bad. That's bad because nobody knows what your code does. And you could be sending it out there to do gosh knows what. I mean, that's how the artificial intelligence takeover is going to happen. Nobody knows what the code's doing, It's like a science fiction nightmare. So anyways, yeah, figure out a way to get it right the first time. Don't just guess. Okay, that's enough of my rant. Been watching too much sci-fi. Okay, so let's call it quits there. Thank you for watching as usual, and I'll see you next time.